Hello, my name is Niklas Grimm, and I will present you today our paper Language-Based Web Session Integrity. This is a joint work with Stefano Calzavara, Riccardo Focardi, Matteo Maffei, and Mauro Tempesta. As we want to talk about web session integrity, let me first introduce the concept of a web session and how authentication works in web apps nowadays. So here we have a user Alice that wants to transfer money using online banking. So Alice types in her browser bank.com, and the browser sends the request to the server. The server then responds with a login page requesting Alice to input her username and her password. When she does so, the browser will send these parameters to the server, and the server can check in its database that the password secret is indeed a valid password for the user Alice. And then it can respond with a welcome page, allowing Alice to do further actions. In addition, however, it will include in the response a so-called session cookie, which is a random token that will from now on serve as an additional authentication mechanism for Alice. So instead of providing her username and her password, it is sufficient if Alice shows this session cookie. And if Alice now clicks the transfer money button, the browser will send the transfer money request to the bank, and in addition, it will attach this session cookie. So with this session cookie, the server can now check that this request is actually authenticated. However, if this approach is implemented naively, there are a lot of things that can go wrong. For example, let's consider the famous cross-site request forgery, or for short CSF attack. In this attack, we assume that the user Alice already is logged in with the bank and has a cookie stored in the browser's cookie memory. And now, while being logged in, Alice goes to visit evil.com, which is a website controlled by a web attacker. And the browser sends this request to the attacker, and the attacker replies with some benign-looking content. However, in addition, invisible to Alice, the response also contains a piece of JavaScript. This piece of JavaScript calls the browser to send a request to the bank to transfer money. And as to the browser, this request looks perfectly fine. The browser will attach this cookie that it has stored for the bank and send it along with the request. And as to the bank, this looks like a completely normal request. The bank will accept it and transfer money. However, Alice did not intend this and might not even have noticed that this happened. To address these issues, we propose to use a type system for the code of the web server that guarantees the absence of web session integrity vulnerabilities. Concretely, our approach works in the following way. We start with a web application code that we translate into an encoding in a formal model. For this encoding, we have a type system, and for the type system, we prove a theorem that says that if typing is successful, then web session integrity is guaranteed. We then have to enhance our model with label annotations that allow us to precisely express our desired security property. With all these ingredients, we can then start the type checking procedure, and if this is successful, then we get formal security guarantees. And it is important to know that the proof for our main theorem has to be done only once, and we can then reuse the result over and over again. To give you an intuition of how our type system works, I will now present to you one of our case studies, which is the conference management system HotCRP that has also been used to submit this paper. Of course, the code presented here is highly simplified and only covers the aspects that are interesting for the session management. The first endpoint we consider is the login endpoint. It expects a username and a password to be submitted. If they are not submitted, then we simply respond with an empty login form. If they are submitted, then we check that these credentials are actually valid for this service, and if they are, then we start a new session with a fresh session cookie. And then in the response, this session cookie is set in the user's browser, and we include a link to the manage endpoint without providing any parameters. The manage endpoint expects a paper that is to be submitted and a token that is used as CSF protection. It also expects a session cookie to be sent with a request. As a first step, we resume the session identified by the session cookie, and this also restores a session memory that is bound to this cookie. We then check if a paper is submitted. If there is no paper, then we generate a fresh value C token that we store inside the current session. In the response, we then include a form to the manage endpoint, and the value for the paper is left empty, so the user can upload his own paper there. And the value of the token is initialized to the value C token that we just generated. Now, if a paper is actually submitted, then we first check that the token that is submitted is equal to the token that is stored in the session memory. And this is used as a protection against cross-site request forgery. And if the check is successful, then we have the security assertion auth paper user. And what this security assertion models is the change of the server state, which now says that the paper is registered in the account of user. We can now formally define our web session integrity property. And for our property, we require that whenever we have a sequence of security assertions that can be triggered in a run of the system where the attacker is present, then the same sequence of security assertions can also be triggered in a run of the system where the attacker is not present. So intuitively, this means that the attacker cannot cause any security assertions to be triggered that could not also be triggered in the run without him. I will now show to you how this property is violated by the HotCRP example that we just looked at, and concretely I will show you how it is vulnerable against the so-called login CSF. Here in this example, you see on the left side a run with the attacker, where the attacker controls one of the web servers, and on the right side you see a run without the attacker. In both cases, we assume that the user is already logged in into the HotCRP server and that he has a cookie stored in his browser. Now assume that the user sends a request to the attacker server. So on the left side, the attacker responds with a piece of JavaScript, and on the right side, the attacker is not present, so the server just responds with any benign content. Now this piece of JavaScript on the left side causes the browser to send a request to the HotCRP server. And this request is a login request with the attacker's credentials. So what happens is that HotCRP accepts this request and accepts the login. And as a result, it responds with a session cookie for the attacker's account that is stored into the honest user's browser. So instead of being logged in his own account, the honest user is now logged into the attacker's account. Now, if the user uploads her paper, then on the left side, it will be stored in the attacker's account, and in the right side, it will be stored in the user's account. So the security assertion that's produced on the left side is the paper with the attacker's identity, while on the right side, we have the paper with the honest user's identity. So we clearly see how the security assertions differ and how this breaks the security property. Next, I want to talk about labels in our framework. Labels are of the form HTTPD or HTTPSD, or can be a combination of these simple labels. Labels are then used for information flow policies and can be used for confidentiality, to express who may learn the content of a given resource, or for integrity, to say who may influence the content of a resource. These labels can also be used to model capabilities of an attacker. So for example, if we consider a web attacker that is an attacker that has control over a domain D, then his capabilities would be the following. He can read any traffic, encrypted or unencrypted, that is part of a communication to this web server D, and he can inject any message, encrypted or unencrypted, into this traffic that is part of the communication with the server D. As a second example, a network attacker can read any unencrypted message that is part of any communication with any server, and he can also inject any unencrypted message into any communication with any server. Next, I want to give to you an overview of the ingredients that we use for typing. You can see here a typing judgment that we use for server-side code. We have a typing environment gamma that gives types to references and URL parameters. We have a session label that limits the labels of session variables. So, for example, if an attacker can learn the session cookie, then it does not make sense to store secrets inside this session. We have a PC label that tracks the integrity of the control flow. The typing is parametric by the attacker label and it tracks the capabilities of the attacker. We have the code that we want to type check. And finally, we have the resulting session label and the PC label that are used for typing the continuation. Also, we have to type the code twice using different assumptions that correspond to two different scenarios. The first scenario is the honest case, where the user just normally uses his browser to interact with the website. And the second case is the CSF case, where the attacker uses some piece of JavaScript to cause the user's browser to send requests on his behalf to the server. In both cases, the types of the cookies come from the environment gamma. This is because in both cases, the cookies are sent from the honest browser's cookie storage. For the PC label, we have a high integrity control flow in the honest case because it's an intended control flow. And in the CSF case, we have a low integrity control flow because it's not intended. And for the URL parameters, in the honest case, we give the parameters types according to the environment gamma, while in the CSF case, the parameters have low integrity and low confidentiality since they have been selected by the attacker. With this information, we can now revisit the example and try to type check it. To type check our security assertion, we require a high integrity session, high integrity control flow, and high integrity parameters. So if we look at the session here, this has to be high integrity. So we also need a high integrity session cookie. However, if we look at the login endpoint where the cookie is set, so to set this high integrity cookie, we need a high integrity control flow. However, we know that if we type check this code under the CSF assumption, then the integrity of the control flow is low. So this is where typing fails, which is also expected since we found the login CSF vulnerability, which has exactly the effect of setting a new session cookie. So it makes sense that we cannot give high integrity to the session cookie. To address this issue, we implement the following fix. We introduce a so-called pre-session. So if no username and password are provided, we start a new session with a fresh session cookie. And inside this session, we store a fresh random value C token. And in the response, we set this cookie in the user's browser and we supply the login form where the username and password are left for the user to fill in. But as an additional parameter, we provide this C token that we just created for the session. If a username and password are provided, then we first resume the pre-session and then we check whether the token that is provided as a URL parameter matches the token that is stored inside this pre-session. In an honest request, these tokens will match by design because this is how we introduced them in the previous step. An attacker, however, who tries to mount a CSF attack has no idea what the value C token in the session is, so he cannot provide the matching token and he cannot pass this check here. So let's now take a look at how this affects typing, and we start with the CSF scenario. In the CSF scenario, we have a low integrity control flow and we have parameters that are of low confidentiality and integrity since they are provided by the attacker. We can then type this block of code with high confidentiality and low integrity. We need low integrity because the control flow is of low integrity, but it is okay to use high confidentiality since the reply will always end up in the honest user's browser, and there is no way for the attacker that is mounting the CSF to learn the content of the response. So the token and the cookie are of high confidentiality but of low integrity. If we now look at the token check, we have the following setting. We have the token, which is the URL parameter, which is of low confidentiality, and we have C token, which is the value that is stored in the session, which is of high confidentiality. And since this is a mismatch, we can statically determine that the check will always fail, and hence we don't have to type check the continuation in the CSF case. So this case type checks fine. Now if we look at the honest case, here we have a high integrity control flow and we have parameters that are of high confidentiality and integrity. Actually, the token is of low integrity, which is according to the environment gamma that we have. And just as in the CSF case, we can type check this block of code with high confidentiality and low integrity. And it is fine to type check this code with low integrity, even though we have a high integrity control flow. And this is because of subtyping. So if we look at the token check now, we have the situation that both tokens are of high confidentiality. So the check may succeed and we have to type check the continuation. So for type checking the continuation, we can use high confidentiality and high integrity, since we have a high integrity control flow for the honest user. And in particular, we can give high integrity to our session cookie. I will not present the typing for the manage endpoint, but having high integrity for the cookie is enough to make it work. Using our theorem, this then shows that web session integrity is guaranteed for this code. So now we show that web session integrity against a web attacker is guaranteed by using typing. However, if we consider stronger attackers, they can still perform other attacks. For example, if we consider a related domain attacker, he can perform cookie forcing, which is an attack where the attacker forces an arbitrary cookie into the victim's browser. This can, for example, also be used to log the user into the attacker's account. In this case, we were even able to use cookie forcing to mount a session fixation attack, which in the end allows an attacker to log in into the victim's account. To conclude, I would like to give an overview of the contributions in our paper, some of which I didn't speak much about in this talk. First, we define a formal model of a web ecosystem, which includes a small step semantics for server and browser. We provide a type system for sound verification of session integrity, which includes typing for server commands and browser scripts, and also a full proof of the security properties. Finally, we applied our results to 3 different case studies, where failure in typing allowed us to uncover novel vulnerabilities. In these cases, we then proposed fixes and used typing to prove their security.